Hello. In this video, I'm going to apply the framework of hypothesis testing to another example, which is a simple and interesting example. So suppose that I'd like to test my belief. I believe that students spend 30 hours to study for midterm exams on average. I don't know if it's underestimation or overestimation. But say, like an average student takes like 5 to 6 courses, and I think they study like 5 to 6 hours per course for the midterm exam. Or so anyhow, so I don't know, no one knows. So anyhow, I believe that students study 30 hours on average for midterm, and to test my belief, I random sampled 100 students and asked them and watched them how many hours they study for the midterms. And what I found was actually the sample mean was 31 hours. So out of the 100 students who I surveyed, their average was 31 hours. And the standard deviation within them were 10 hours. And so what I'm going to do is I believed 30, but the data like it's saying 31. And then do I need to reject my belief or not? So there are two possible scenarios. One, the data is similar. 31 hours is pretty similar to 30 hours, so my belief is not wrong, approximately correct. So it's consistent. Still, it's consistent with the data. Just the data have some noise, random errors. So the difference of 1 hour is nothing. It's just noise. That's one possible argument. And the other possible argument is that no, 1 hour difference is huge. So you believed 30 hours, but the data says different number, 31 hours. So 1 hour difference is huge, so it cannot be a noise. It's a significant difference, so you have to apologize to the students. They are studying more than you think. Uh, uh, I don't know, like, so both are possible. So we are going to choose which is the correct argument statistically. So I will show you how to do that. And we are going to use significance level at 5%. So it's your choice. Like you choose confidence level, you are choosing the significance level whatever you like, but 5% is the most standard one. So I'm going to stick to that. So 5% is chosen. And what I'm going to do first is to formulate the hypothesis. It's simple. In our statement, it's clear that the null hypothesis is mu. Mu is the expected study hours. Expected study hours is 30 hours. But the alternative hypothesis is simple negation of that. Right? It's still possible. You can simply use the negation of the null hypothesis as the alternative. And here, underlying random variable is x, which is the midterm study hours for a randomly chosen student, right? And then mu is the expected value of x. This is the statistical formulation of the hypothesis. And then we are going to consider how can we measure the difference from the data and to your belief. So that is the test statistic. Earlier I explained it as a suspiciousness, but now maybe a better way to describe it now is the difference between the data and your belief and my belief. So we are going to use the sample mean. Sample mean can be compared to my belief. It's right. In some sense, it's obvious, right? Because I have a belief about the population mean, and then its best estimator is the sample mean, which will be a good comparison counterpart to my belief, right? So we are going to use the X bar as the test statistic. So we will see if X bar is, so if X bar is too much different from my belief, then I'm going to reject my belief. That's the role of the test statistic. So it gives the measure so that we can reject based on that, right? That is the test statistic. And what's more complicated is here. Okay, we are going to use the sample mean, and then now we need the distribution of it. The sampling distribution of the test statistic if the null hypothesis was true, right? That's actually easy in this case because we know the central limit theorem. The X bar, the sample mean, has a very nice property of the central limit theorem. So it follows a normal distribution with mu and sigma squared over n. And like what we need to know is the mean and the variance. Sample size is already known. It's 100. I surveyed 100 students, so it's not a problem. Then how also the mu is actually fixed because we believe that my belief is 30 hours. So we are going to use that. 30 hours is my belief, so it will be believed until the data has contrast to my belief. So yet I'm going to use 30 hours, my belief, as a parameter. So my parameter is determined. And then the only unknown is the standard deviation, the variance. I will simply use the sample standard deviation in the place of the unknown standard deviation. So it's simple. We will get the sampling, the null distribution, which is the sampling distribution of the test statistic under the assumption that the null hypothesis is correct, right? So it's using the central limit theorem, we get this. And remember, we have to use the null hypothesis to specify the parameter. And that means if my belief was correct, then the mean is 30 hours, right? Mean is 30 hours, but because of randomness in random sampling, my survey I may have encountered some like more hardworking students than the average. So then 31 hours is possible, like statistically possible. Or if I redo it again, if I resurvey again, I may get 28 hours. That's possible, always possible. As I said, in statistics, things are possible, but just probability is too small. Like say, but if my mean is, say, for example, even if the mean was 30 hours, but in an extreme case, I may get 100 hours if there was a huge error. Like say, I wrote down a different number or put another zero in recording the outcomes. So for example, so anyhow, what's important here is it's not about possible or impossible, but it's about likely or not unlikely. So the outcome becomes less likely as it moves away from 30. So this direction or this direction, both directions make the outcome unlikely. Earlier, I explained it as suspicious. Become more suspicious in two directions. In both directions, they are equally suspicious. So far, I do not use 31. The observation has 31 as the sample average, but we did not use that. Now we put our observation in this distribution. To this distribution, if I put my observation, it is located here. Now what I have to do here is I have to calculate how suspicious this guy is, how uh, how how much different from my belief. The difference from my belief is measured by the probability of more suspicious guys, probability of less likely outcomes. Then it goes like this. What's interesting here is, so I observed 31. So obviously this 31 or higher are the outcomes less likely or more suspicious or more different from my belief. That's obvious. But you have to remember that equally unlikely outcomes exist on the other side. So 31 or higher is equally unlikely as 29 or lower. So because it's symmetric, so this tail is unlikely as much as this tail is unlikely, the other tail is equally unlikely. So as I said, suspiciousness increases in both directions. So when you calculate the ranking, these guys are more suspicious or more different from my belief than what I observe, right? So we are going to calculate these two areas for the p-value. The p-value is the probability on this blue shaded area. How can we calculate that? It's simple algebra. We spent like 2 or 3 chapters to do this. Still, I understand you need more exercise, but so if you are not certain what I'm doing, then I recommend you to go back to chapter 6 and chapter 7 are important preliminary chapters for this one. So p-value, we just learned that the p-value is smaller than 29 or greater than 31. So, and what we are going to do here is we are going to standardize x bar into standard normal distribution. And when you standardize, the other side has to go in the same way, has to be changed in the same way. So the right hand side of the inequality should be subtracted by the mean and divided by the standard deviation. And same thing here. And you know how to calculate that. So this part, this guy, this was 30 because I believe my belief is correct, right? So 30 is here, and standard deviation is the standard deviation for the sample mean. So 10 divided by the square root of sample size. Same thing here, same parameters are used here. And then you calculate, in the end, you have probability z smaller than -1, greater than 1, and you can calculate these probabilities from a standard normal calculator. Z is a standard normal distribution, so you can calculate them using any calculator or Excel, any program. So this is the p-value. This is the p-value. But another useful thing we usually use is the t-statistic. So we use the t-statistic in many cases, which is simply the standardized sample mean. So test statistic is the sample mean, but when you use the test sample mean as the test statistic, it would be more convenient to standardize it at the beginning. So if you standardize the observed sample mean, then you subtract the mean and divide by the standard deviation for the sample average. You will get 1. Then actually we are doing the same standardization process here here, same standardization process here, in just outside of the parentheses, right? So when you calculate the sample mean, do a little more algebra and standardize it so that it's more convenient to calculate the p-value. So once you get the t-statistic, then p-value is calculated in this way. Again, you have to consider the other side of the distribution because the other side is equally unlikely. So standardization process is separated out, and we defined this guy as the t-statistic. So then automatically the t-statistic follows a standard normal distribution, so you don't need to change that into the standard normal distribution again. Okay, then in the end, whatever you use, p-value is 31.731%. So p-value is 31%, which means within the ranking, so the top is the most suspicious or the most different from my hypothesis, and down to the least different outcome from my hypothesis. And your observation, 31 hours is at 31% level from the top 31%, which is pretty low ranking because the significance level was 5%. It means I'm going to reject only at the top 5%. But your observation is 31%, which is much lower than your standard. Therefore, you cannot reject my hypothesis. So then it means that the observed outcome, 31 hours, is sufficiently plausible, likely enough, even if my belief is 30 hours. So I believe that students study 30 hours, but I observe 31 hours. The 1 hour difference is just a noise. That's likely. It's a likely noise, likely random error. So why do we reject my hypothesis? It's just random error. We can ignore that. That's our conclusion from this example, right? I hope this example shows a better framework to understand the hypothesis testing. In the next video, I will consider even more generalized framework for the hypothesis testing. But basically, we are extending our framework to the most general case. Okay, thank you for watching and see you in the next one.